Did you know that when a fuel burns, it's being oxidized because the fuel is combining with oxygen from the air? We're going to take a look at other definitions of oxidation, reduction, and combining the two to call them redox reactions. So, this topic is all about oxidation and reduction. In this video, we're going to look at the concept of oxidation, reduction, and redox reactions, also known as redox. So what you need to be able to do for your exam is define a redox reaction in terms of oxygen or hydrogen transfer, and then go on to define a redox reaction in terms of electron transfer, that's electrons being gained or lost. And then are you able to define a half equation? So this comes from your specification reference 3.1.7. So any reaction in which oxygen is added is historically known as oxidation. So this is where reactions are gaining oxygen. So in this equation here, you can see that copper is gaining oxygen to form copper oxide. The copper is being oxidized because it's gaining oxygen. Reduction, on the other hand, describes a reaction where oxygen is taken away. So in this reaction, the copper oxide loses its oxygen to form copper again, and hydrogen is taking the oxygen away. So in this respect, hydrogen is known as the reducing agent because it's taking oxygen away from the copper oxide. So let's now look at a short video clip in which oxidation and reduction using oxygen and hydrogen takes place simultaneously. At this point, I really apologise for the choice of music. In this video, the word reductant is the same as reducing agent. In the video, you saw the Roxil wool, not cotton wool will have combusted, being heated. One other apparatus problem there was that the clamp was in the middle of the tube, and the clamp, if it was made of rubber, would have burnt. It should really have been clamped near the neck of the boiling tube. But apart from that, let's look at the chemistry behind the reaction. The magnesium in the reaction took the oxygen away from the water. So we can say that the magnesium is the reducing agent. That's the species or the agent that's taking away the oxygen. Steam, on the other hand, is what is providing the magnesium with its oxygen. So the steam in this case, or the water, is the oxidizing agent. We can see that on this side of the equation, magnesium has gained oxygen and therefore it's been oxidized. The steam has lost its oxygen and therefore it's been reduced. So the reducing agent gets oxidized and the oxidizing agent becomes reduced. So let's now look at a quick video of magnesium just burning in oxygen.
Form of light and heat, but a brilliant white light. So you can see this here, bring the lights down please. So a brilliant white light as the magnesium reacts with the oxygen from the air. And if we have the lights back up for a moment please, well, you can see the smoke.
From the video, you could see that magnesium, as it combined with oxygen, gave out lots of light and heat to form the white solid magnesium oxide. But let's look at what happened to the magnesium atoms and the oxygen atoms individually in terms of electrons. The magnesium transfers 2 of its electrons to the oxygen atom, forming magnesium ions and oxide ions. Electron transfer has taken place. We can now write this as what is called a half equation. The half equation shows the reducing agent here, magnesium, losing its electrons to form positively charged magnesium ions. This is an example of a half equation. It's usual to show the electrons as being added to either side. So we can see that the magnesium has been oxidized because it has lost electrons in this half equation. The oxygen gains 2 electrons, as we can see here, but we're dealing with oxygen gas. So we're dealing with oxygen gas, and therefore we can see that the oxygen, because it goes around as molecules, so we must write it as its elemental state, as we can see here, has gained 2 electrons. This is represented by the O2 minus on this side. So in this case, we can say that the element oxygen has been reduced because it's gained 2 electrons. So to summarise, we can say that oxidation is loss of electrons and reduction is gain of electrons. Reducing agents lose electrons, oxidising agents gain electrons. So it's important to remember that an oxidation is where electrons are lost, reduction is where electrons are gained, but an oxidising agent gains electrons and a reducing agent accepts electrons. So oxidation is loss, reduction is gain, and that's either of electrons or hydrogen. Let's now make the idea of oxidising and reducing agents more simplified. So if we consider this ladder, the ladder of oxidation and reduction, and we place magnesium on level 0, when magnesium lost 2 electrons, it moves up the ladder because it gains positive charge and it threw away 2 electrons. So moving up the ladder, you're becoming oxidized. Whereas oxygen, on the other hand, gained electrons and moved down the ladder and therefore became reduced. We can either see the magnesium as being the bad guy here, like a drug pusher, and pushing its E's onto the oxygen. So the species that's getting oxidized and going up the ladder is sending someone else down the ladder. The species that gets oxidized is the reducing agent. Oxygen, on the other hand, took the E's. It took 2 E's and got reduced. It goes down the ladder. So oxygen, therefore, is the oxidizing agent. The oxidizing agent is the species that takes electrons. Thus, the oxidizing agent is the species that takes electrons. Thus, your reducing agent is the species that gives you the electrons. So the reducing agent gives or donates the electrons. So if we look at the half equations where magnesium is being oxidized and oxygen is being reduced, we can now combine the 2 half equations by bringing both sides down and adding them both together. So on this side we have magnesium plus half a mole of oxygen molecules plus 2 electrons. And on this side we have magnesium ions and oxide ions and 2 electrons. And what we can do, because the electrons are appearing on both sides, is take 2 electrons from this side and 2 electrons from this side. So the equation now simplifies as magnesium added to half a mole of oxygen molecules makes 1 mole of magnesium oxide solid, and in the overall redox equation, where oxidation and reduction has occurred simultaneously, the electrons never appear in the final equation. Now try the following summary equations, which are from your Caboodle textbook. So in each of them, write your answers out and pause the video before checking your answers in the next section. Pause the video now. You can see that the metal calcium has lost electrons and has therefore become oxidized. And that happens to all metals. Metals tend to lose electrons to become oxidized. The bromine is a non-metal element, and bromine molecules have gained electrons and have therefore become reduced. And non-metals tend to gain electrons to become reduced. So calcium goes up the ladder, donating its 2 E's to form calcium ions. And the bromine in this case has taken those 2 E's and it's gone down the ladder to form 2 bromide ions. So it's taken those 2 E's to form bromide ions. And therefore, remember, the reducing agent was the species that pushes the E's. So in this case, the calcium is the reducing agent, and the bromine, because it's taken the E's, is the oxidizing agent. And a rule of thumb is non-metals, which are on the right hand side of the periodic table, tend to be the oxidizing agents. So non-metals tend to be oxidizing agents, and metals tend to be the E dealers, the electron pushers. So metal atoms tend to be reducing agents to form metal cations. And non-metal molecules tend to be oxidizing agents, forming non-metal anions in the electron transfer. We're now going to look at the concept of oxidation states, in some textbooks also known as oxidation numbers. So don't be confused if you see the two. Oxidation states is interconvertible with oxidation number. So from the syllabus, you need to be able to define what is meant by an oxidation state and define and describe how you work out oxidation states. From your textbook, it tells you that oxidation states are used to see what's been oxidized and what's been reduced, because it's not always apparent. Not all equations are simple electron transfers. Now here's a list of rules that could destroy even the least faint-hearted. I'll just quickly go through these rules, but it's a lot better if we actually practice them by doing some examples. But let's go through these rules quickly. So first of all uncombined elements have an oxidation state of 0. Pause right there. It's always best to go back to our ladder. So let's now reword that. Uncombined elements have an oxidation state of 0. Well, we saw that magnesium and bromine in the last example both happily sat on the ladder of 0, and that's because they've got no charge. So that's a lot easier to remember. All elements have an oxidation state of 0. The next rule is some elements always have the same oxidation state in all of their compounds. So let's look, for example, here. Magnesium is in group 2, and magnesium, all it can ever do is exist on 0, or it can exist as Mg2 plus ions. There's no other oxidation states for magnesium. It's either 0 as the element or plus 2 as the ion, because it can only ever lose 2 electrons. Aluminium also can only ever lose 3 electrons. So when aluminium goes up the ladder, aluminium is in group 3, and therefore it can only ever give away 3 electrons to go to plus 3 on the ladder, losing 3 E's. So all group 3 elements are always plus 3. So basically, the charge on the ion is exactly the same as the oxidation state. Now oxygen is always -2, and let's see oxygen here. Again, it's a non-metal, and oxygen therefore can only ever go down to form oxide ions. There's one exception which we'll get to later. And fluorine, also a non-metal, can only ever go down to -1 because it's in group 7 and it can only ever gain 1 electron. So it can only ever form fluoride ions. The charge on the fluoride ion is -1 and that's its other oxidation state. So fluorine can only ever exist as 0, as it is here with all the other elements from the periodic table. And because it's in group 7, it can only ever gain 1 electron and it can only exist as fluoride ions. And that's why its oxidation state is exactly the same as the charge. Chlorine, on the other hand, is like fluorine, it's in the same group, can form chloride ions, but what we'll see later is it can also share its electrons and it can also share more than 1 electron. And we'll look at that later. Now, the most obvious one that doesn't look obvious here is when you add all the oxidation states together in a compound, there should be no overall charge. And we saw that before when we had our magnesium 2+, and our oxygen with its oxidation state of 2-, that's got an oxidation state of +2, that's got an oxidation state of -2 because it's the same as the charge on the ion. The overall compound has got no overall charge. So when you add +2 and -2 together, they cancel out. So the compound should have no overall charge. So let's just add the other two rules in for good measure. The sum of the oxidation states of a complex ion, well, they're not complex ions, these are called common ions. So you've met ammonium before and you've met sulfate before, and these, all the oxidation states equal a charge on the ion, and we're going to walk through those in a moment. Now, the most important one, I think, is in a compound, the most electronegative element, and that's usually the non-metal element. But what about when you've got two non-metals? The most electronegative element, you always give the negative oxidation state. So rather than try and remember these, let's do some examples. So here's an exercise from your Redox pack in college. And what we'll do is walk through each one in turn. So the first one says, calculate the oxidation state of sulfur in sulfate. Let's do that now. So what do we know about sulfate? Well, this is where you need to know some of the rules. First of all, the rule is the sum of the oxidation states of a complex ion, a common ion, equals the charge on the ion. So the charge on the ion is equal to 2-. Let's write that down. The sum of the oxidation states is equal to the charge on the ion. Now we don't know sulfur, so I'm just going to write that as S. But we do know from our rules that oxygen is always has an oxidation state of -2. But we have not got one oxygen or atom in the sulfate ion, we have 4. So what we do is we say, well, that's 4 lots of -2. Because we know that the oxidation state of oxygen is always -2. So sulfur -8 equals -2. That's the overall charge on the ion is the sum of the oxidation state of sulfur and 4 lots of oxygen. How do we get rid of the 8? We add 8 to both sides. So that's sulfur on its own now, -2 add 8. And therefore that tells us that sulfur has an oxidation state of +6. Well, that makes sense since sulfur is in group 6 of the periodic table and it has 6 outer electrons, which means it can share all of these electrons. Notice its oxidation state is +6, even though it's sharing 6 electrons, because oxygen is the more electronegative element. Pause the video here and write down that example. Let's now find the oxidation state of nitrogen in the nitrate ion. Using the rules again, the sum of the oxidation state are equal to the charge on the ion, and this time the charge on the nitrate ion is -1. So the sum of all the oxidation states is equal to -1. We're trying to find nitrogen, And we know from our rules that we've learnt back to front that oxygen always has an oxidation state of -2. So there's 3 oxygen atoms, so that's 3 lots of -2, and the sum of the oxidation states is -1. And therefore nitrogen -6 has an overall charge of -1. How do we get rid of the -6? We add 6 to both sides. So that's -1 plus 6. So in this case, nitrogen has an oxidation state of +5. Well, that makes sense because nitrogen is in group 5 of the periodic table and has got 5 outer electrons which it can share. Oxygen is more electronegative, so that always acquires the more negative oxidation state. So in nitrate, we say that nitrogen has an oxidation state of +5. We call this the nitrate 5 ion, and that is because the nitrogen atom is sharing 5 of its electrons and its oxidation number is +5. So the Roman numeral after the name of the ion denotes the oxidation state of the other non-metal or the less electronegative non-metal atom. Nitrogen is +5. Let's now go and look at chlorine in ClO3-. Make sure you pause the video to write this down. So what about the oxidation state of chlorine when it's combined with oxygen in this ion? And how do we name this ion? So first of all, again, the sum of the oxidation states of chlorine and 3 lots of oxygen, which we know have an oxidation state of -2, equals the overall charge on the ion, which is -1. So chlorine -6 equals -1. Add 6 to both sides to get rid of the -6, and that therefore leaves chlorine with an oxidation state of +5. But Wendy, you might say, chlorine is in group 7. But if we write out the electron configuration of chlorine, the outermost electrons in the third energy level are 3s2, 3p5. And that means that chlorine in this case is sharing its 5p electrons. How do we name this ion? Well, any ion that contains oxygen ends in 8. So we know that this is going to be a chlorate ion. And because it's got an oxidation state of 5, that is known as the chlorate 5 ion. 8 because it contains oxygen, 5 because that's the oxidation state of chlorine. Chlorine gets the more positive value because oxygen is more electronegative than chlorine. So here's an example of chlorine with its oxidation state higher than -2. Pause the video while you write that down. Let's now look, I'm going to jump to E, chromium in dichromate. Again, the sum of the oxidation states is equal to -2. So we don't know chromium, but there are 2 chromium atoms in chromium. And that is added to 7 oxygen atoms, and we know that oxygen always has an oxidation state of -2. So 2 chromiums minus 14 is equal to -2. We add 14 to both sides, and that's -2 plus 14. 2 lots of chromium have an oxidation state of +12. We divide both sides by 2, and that means chromium in this case has got an oxidation state of +6. That makes sense because if we go to look at chromium's electron configuration, remember it's 3d5 4s1. It has a total of 6 electrons in its highest energy level, and it can involve all in bonding, sharing 6 of those electrons with these oxygen atoms here. So the name of this ion is the dichromate 6 ion. Dichromate 6 because it's sharing its 6 highest energy electrons. Di because there are 2 chromium atoms as opposed to the chromate ion, the chromate 6 ion, which has the formula CrO42-. That is the chromate 6 ion. It has exactly the same oxidation state of +6. So this is the dichromate and this is the chromate ion. Pause the video while you write that example down. Let's now look at example H, manganese in MnO2. So manganese in MnO2. Now this time there is no charge. It's a neutral compound. So the overall charge on the compound is 0. We're trying to find manganese and it's combined with 2 oxygens. So the sum of their oxidation states is 2 lots of oxygen, which is 2 times -2. The overall charge is 0. And therefore, manganese -4 when you add the 2 together equals 0. So the oxidation state of manganese, if we add 4 to both sides, is +4. Let's do K in this weird looking what's called a complex ion. So copper in Cu-H2O6 brackets 2+. Well, the overall charge on the ion is equal to +2. We're trying to find the oxidation state of copper. Now this time we know, without working out the oxidation states of all the elements, that water molecules have got 0 charge. So we can simply say there are 6 water molecules with 0 charge. 6 times 0 is a big fat 0, and therefore copper has got an oxidation state of +2. Let's do a final one. Copper in CuCl4 2-. The usual rules apply. So this time the overall charge on the compound is on the ion is -2. We're trying to find copper. What do we know about chlorine from our rules? Well, chlorine, when it's combined with a metal, is always -1. So that's 4 lots of -1. And therefore copper -4 has an overall charge of -2. If we add 4 to both sides, therefore that becomes +4. -2 + 4, copper has got an oxidation state of +2 again. So what we're going to do now is look at this, what looks like a complicated equation. And the question says, look at each of the species in this complicated redox equation and decide which species have been oxidized and which species have been reduced. So we can simply do this by working out the oxidation numbers of each of the species. Let's go through each one in turn. So let's take the first one. Now the first one contains, as you can see here, iodine and oxygen. So what's happened to the iodine on this side? Well, it must have become I2. So the I in this ion here, this iodate ion, has become iodine. So we can write an equation to show the iodate becoming iodine. And we can work out the oxidation number straight away of this because it's a pure element. And we know from our ladder that pure elements have got an oxidation state of 0. They're sitting right in the middle of the ladder with an oxidation state of 0. So let's use our rules that we just did to work out the oxidation state of the iodine in iodate. So therefore, remember it's equal to the sum of the charges of the oxidation state gives the overall charge on the ion. We know that oxygen is -2 and there are 3 of them, so that now equals -1. If we add 6 to both sides, iodine in this case has an oxidation state of +5. Iodine has gone from +5 to 0 and it's gone down the ladder. We can say that the iodine in this compound has been reduced. Now, If iodine has been reduced in iodate, and we can now name that ion, we know that's now the iodate 5 ion because the iodine has an oxidation state of +5. Let's now see another element. So let's now look at hydrogen. Hydrogen here and hydrogen here. Well, the rule is when hydrogen is combined, it's always got an oxidation state of +1. So now let's go to the sulfur. Notice I'm going to ignore these big numbers here. We're simply concentrating on the charge on the ions. So the HSO3 minus ion, well, we know from our rules that hydrogen is always +1 when it's combined. We know that oxygen is always -2. And we know that the charge on the sum of the oxidation states is the charge on the ion, which in this case is -1. So hydrogen is +1, so we can write that in. We don't know what the sulfur is, so we'll leave that as sulfur. And we also know that oxygen is -2, and there's 3 lots of them, so that's -6, giving an overall charge of -1. Sulfur -5 is equal to -1. Let's now add 5 to both sides, and sulfur has got an oxidation state of -1 plus 5. Sulfur has got an oxidation state of +4. So let's write that over the sulfur in this hydrogen sulfate ion here. That's going to be hydrogen sulfate 4. So we've now established that iodine over here is 0. Let's now see what sulfur has become here in the SO4 minus ion. So when the sum of the oxidation states of sulfur and oxygen are added up, the overall charge in the sulfate ion is -2. Sulfur -8 equals -2 because there are 4 oxygen atoms. Sulfur, let's add 8 to both sides, therefore has got an oxidation state of +6. So it's gone from +4 to +6. Oxygen has climbed up the ladder, and when you climb up the ladder, you have become oxidized. You can see that sulfur has lost 2 electrons because it's gone from +4 to +6. So let's now write the oxidation state of sulfur over it there. Hydrogen hasn't changed because it's +1, +1, and oxygen is -2. So the only 2 elements to change oxidation state in this reaction are iodine, which has gone from +5 to 0. It has become reduced and gone down the ladder. The sulfur has gone up the ladder because it's gone from +4 to +6. Now remember, the species that becomes reduced has taken E's. It's taken E's away, and therefore we can say with all certainty that the IO3 minus ion is the oxidizing agent because it has become reduced. It's taken E's. We can see that the sulfur in the HSO3 minus ion is the reducing agent. So the HSO3 minus is the reducing agent because it has given up its E's, it's donated its E's, it's pushed its E's onto the iodate, and it itself has gone up the ladder from +4 to +6. So the HSO3 minus is the reducing agent. And we've worked this out by looking at oxidation numbers. Notice in the equation also that the hydrogen atoms haven't changed their oxidation states, nor have the oxygen atoms either. So the species, the agents, always appear on this side of the equation. The reducing agent is the iodate 5, and the oxidizing agent, the species that's taking the electrons, is this, and the reducing agent, again appearing in the reactants, is the HSO3 minus ion, and therefore this is a redox reaction because the oxidizing agent, the iodate ion, gets reduced to iodine, and the HSO3, the hydrogen sulfate 4 ion, becomes oxidized to the sulfate 6 ion. Therefore, this is the reducing agent. So the oxidizing agent and reducing agent always appear on the reactant side, always on this left-hand side. Where you've got an oxidizing agent, you will always have a reducing agent. So look at this short video clip and let's decide which species has been oxidized, which is reduced, which is the oxidizing agent, and which is the reducing agent.
Talk me through what's going on, mate.
So instantly the thermite reaction starts and you can see that it's so hot it's burnt a hole through the bottom of that terracotta flower pot. But if we go in close...
This reaction is known as the thermite reaction, and this is a reaction that takes place to weld railway lines together even today. So let's look at the equation. You have aluminium powder mixed with iron oxide or rust. When they react together, this white solid of aluminium oxide is produced, plus molten liquid iron you can see falling from the pot here. So let's have a look in terms of redox, what's happening in this equation. Well, first of all, if we look at the aluminium, it's got an oxidation state of 0 because it's an element, and so has iron on the other side. Let's now look at the oxidation state of aluminium within the aluminium oxide product. So we'll work out its oxidation state as we've always done. We know that the overall charge on the aluminium oxide is 0. So when we add the aluminium and the oxidation state of aluminium plus oxygen together, we'll get an overall value of 0. Now we know oxygen is -2 always when it's combined. So that's 3 lots of -2, which is -6, equals 0. If we now add 6 to both sides, then the overall charge is +6. Dividing that by 2, it's not surprising then that the oxidation state of aluminium is +3 because it's in group 3. So aluminium has gone from an oxidation state of 0 to +3. It has gone up the ladder, and therefore it has become oxidized and given up its electrons and pushed them onto the iron oxide. Can you see now the aluminium is therefore the reducing agent as it's pushed its electrons. Metals are usually reducing agents, and when you see elements in any equation, you know it's a redox reaction. Let's now look at the oxidation state of the iron using the same principles. There's no charge on iron oxide, so therefore with 3 oxygens the overall charge is +6, and therefore iron has an oxidation state of +3. The iron then has gone from +3 all the way down to 0, and therefore we can see it's gone down the ladder, and therefore it has been reduced. So the iron oxide, because it's given up its oxygen, is the oxidizing agent. Notice that oxygen has never changed its oxidation state on either side. But let me reiterate, in a multiple choice situation when you're asked which one is a redox reaction, if there is any element on the reactant side, the reaction is a redox reaction. In this next exercise, you are asked to classify the reaction as oxidation, reduction or redox. and in the case of the redox reaction, highlight which species is being reduced and which species is being oxidised. So let's start off with a nice easy one. Here we can see copper is being turned into copper ions and it's losing 2 electrons. Well, we know it's a half equation because electrons are appearing in the equation and only one species. Copper is an element and therefore it sits in the ladder on level 0, and here the charge on the ion is +2 and the oxidation state of an ion is simply the charge on that simple ion, so it's +2. So copper has gone up the ladder, it's given away its E's, and therefore it has been oxidised. This is a full equation and we met it earlier on in the video. We can see here that magnesium is an element, so its oxidation state is 0. Here hydrogen is an element because it goes around in pairs, it's not combined with anything, and it has an oxidation state of 0. Hydrogen, from the rules, when it's combined, always has an oxidation state of +1, and oxygen, when it's combined, always has an oxidation state of -2. Magnesium, when it's combined, because it's in group 2, has an oxidation state of +2. Oxygen, when it's combined, is -2. So let's consider the elements on their own. Magnesium has gone from 0 to +2. Magnesium has gone up the ladder and given away 2 E's, and therefore magnesium has been oxidised. On the other hand, hydrogen here has gone from +1 down to 0, so hydrogen has become reduced, it's taken E's. It's become reduced because it's gone from +1 to 0, it's gone down the ladder, it's taken E's, and it's being reduced. Carry out the rest yourself and check your answers in the next part of the video. So notice that only the half equations where electrons are involved are either oxidation, so here copper has lost electrons, it's been oxidised, and you can see here that the zinc has gone from +2 to 0, it's a half equation, and that's a reduction reaction. Here the calcium has lost electrons, it's become oxidised, so it's an oxidation reaction. So only in the half equations can you just have oxidation or reduction. Where they're full equations not involving electrons, they have to be redox because you have to have an oxidising agent and you have to have a reducing agent. In this section, I'm going to show you one method of balancing half equations, and that is using charge, not oxidation states. So like balancing equations, your atoms must always balance first. So on the left hand side of the equation we have a lead atom and we have one lead on this side as well. However, we have 2 oxygens. What do you do when you've got oxygen on one side of the equation and not on the other side? The first rule is when oxygen atoms appear on one side of the equation, they appear as water molecules on the other side. And therefore we're going to now add water, but that only gives us 1 oxygen atom. So we have 2 oxygen atoms on the left hand side, so on the right hand side we need to double that, and now that gives us 2 oxygen atoms. The problem is we've now introduced hydrogen into the equation. What do we do with the hydrogen? So when hydrogen atoms appear on one side of the equation as water molecules, they must appear as hydrogen ions on the other side. Well, what can we see here? We have 2 times 2, which is 4 hydrogen atoms, so these must become 4 H+ ions on this side of the equation. Now we are balanced for atoms, but we're certainly not balanced for charge. Let's see what we do with the charge. So remember, here we are checking charges, not oxidation states. On the left hand side we have a positive charge here. But there are 4 lots of positive charges, so the overall charge on the left-hand side is equal to +4. But on the right-hand side, the overall charge, the only charge here is on the lead ion, which is +2. To balance out the charges, you add electrons to the more positive side. We can see that on the left-hand side there is an overall +4 charge. On the right-hand side it's +2. And therefore, to balance the charge, we simply add 2 electrons to this side. Now the charge is +4 minus 2 because every electron carries a negative charge. The overall charge on this side is +2 and the overall charge on this side is +2. We can now see that this is a reduction reaction because the lead has gained 2 electrons. On the other hand, the oxygen has not changed its oxidation state. Let's now balance this equation using the oxidation number method. So, using the oxidation states method, we still need to balance for atoms, so the rules still apply with regard to oxygen atoms. So on the left hand side we still have 2 oxygen atoms, and therefore they must become 2 water molecules on this side. And we still have 4 hydrogen atoms on this side, so they still have to become 4 hydrogen ions on this side. But now, instead of checking charge, we're going to look at the change in oxidation numbers. So same rules apply before. If oxygen is -2, then the overall charge on this compound lead oxide is 0. We know that oxygen has an oxidation state of -2 and it's combined, and therefore that's -4 because there are 2 lots of oxygen. Lead therefore has got an oxidation state of +4, so this is lead 4 oxide. Underneath I have written the oxidation state, not the charge. Now let's look at the left hand side. Here lead has got a charge of 2+, and therefore its oxidation state is +2. The hydrogen in hydrogen ions is simply +1, is its oxidation state, because it's the same as its charge. We know in compounds, when hydrogen is combined, it's always +1 and oxygen is -2. And therefore immediately we can see if lead has gone from +4 to +2, it's gone down the ladder, it's taken 2 E's, it's been reduced. And since it's gone from +4 down to +2, it must have taken 2 E's, and since it's taken electrons, they must appear on the left-hand side. That is the oxidation state method. We're now going to use both methods to balance this equation. So first of all, we're going to use the balancing charge method. So let's start with the atoms. On this side, we have 2 sulfur atoms, and on this side, we have 4 sulfur atoms. We have 3 oxygen atoms, and we have 6 oxygen atoms. So it makes sense, let's balance for the sulfur by timesing or multiplying the S2O3 ions on this side. Now we can see we have got 4 sulfur atoms on this side and 4 sulfur atoms on this side. 2 times 3 is 6 oxygen atoms on both sides. However, if we now check the charge on the left hand side compared to the right hand side, we can see the charge on this side is 2 times 2, which is -4, and on this side it's -2. The rule is you add electrons to the more positive side. The more positive side this time is the right hand side. So therefore, if we add 2 electrons to the right hand side, the overall charge is now -4 on both sides. That is balanced. Let's now do this using the oxidation number method. This is the left-hand side and the right-hand side. So let's work out the oxidation state of the sulfur in S2O3 2-. So 2 lots of sulfur added to 3 lots of oxygen, and we know that oxygen always has an oxidation state of -2 equals -2. And therefore, if we now 2 lots of sulfur is equal to -2 plus 6. So 2 lots of sulfur is equal to plus 4, and therefore sulfur has an oxidation state of +2. Now in the S4O6, again we've got 4 lots of sulfurs and 6 lots of oxygen, so that's -12. Each oxygen having an oxidation state of -2 equals -2. 4 lots of sulfur equals -2 plus 12. 4 lots of sulfur now equals plus 10. And here, if we divide 10 by 4, sulfur has got an oxidation state of 2.5. That's really strange. So this sometimes happens where the oxidation state rule doesn't pay. Let's try another half equation. This time, using our balancing charge rule, we're going to try and balance this equation where chromium in chromate ions is becoming chromium 3 ions. So first of all, let's balance for atoms. On this side, we have 2 lots of chromium atoms, and the only way to balance this is to put a 2 in front of the chromium 3 plus ions on the right hand side. Now let's look at oxygen. Remember before when we had oxygen on one side? Well, it must form water on the other side, and therefore we must have 7 moles of water because there are 7 oxygen atoms. Now we've got an introduced hydrogen, and remember hydrogen has to become hydrogen ions on the other side. So on the left hand side, 7 times 2 is 14, so we must have 14 hydrogen ions on this side. Now we can balance for charge. The overall charge on this side is 14 times 1 minus 2. 14 times 1 is 14. Take away 2, the overall charge on the left hand side is plus 12. On the right hand side, the overall charge is 2 times 3, which is equal to plus 6. And therefore, we need to add electrons to the more positive side. And the more positive side in this case is the left hand side. And therefore, we can say that we need to add 6 electrons onto the left hand side, and therefore now take away 6 from this. So if we now take away 6, the overall charge is now equal to plus 6 on the left hand side and the right hand side. Let's now do this using oxidation numbers. So as usual, we need to balance for our oxygens and hydrogens, and therefore on the left hand side we must have 7 H2Os, and on the right hand side we must have our 14 H+. So now let's look at the oxidation state of chromium in Cr2O7. We use our usual rules. The chromium, the charge on the ion is equal to sum of all of the oxidation states, so that is -2. And therefore 2 lots of chromium and 7 lots of oxygens. Each oxygen has an oxidation state of -2, so that's -14 equals -2. 2 lots of chromium is equal to -2 plus 14, and therefore chromium must have an oxidation state of +6. So this is the dichromate 6 ion that we met earlier on. The oxidation state of chromium on this side is simply the charge on the ion, which is +3. chromium therefore has gone down the ladder from +6 to +3. It has taken 3 E's. However, since there are 2 lots of chromiums on this side, we need to double that, and 2 times 3E, because we've reduced 2 chromium atoms, is 6 electrons. You can choose whichever method you prefer, either the balancing charge or oxidation states. Your task now is to balance these 2 half equations, one using the balancing charge and the other using the balancing oxidation states. Pause the video now, do this on paper and then check your answer. So using the balancing charge method, we can see that the manganese atoms are the same on both sides, but we've got 4 oxygens on this side, and now we need to add 4 H2Os on this side. We've now introduced 4 times 2, 8 hydrogens on this side, so we must balance that by adding 8 H plus ions on this side. Now to check the charge, we have +8 minus 1, which has an overall charge of +7 on the left hand side, and on the right hand side we have a charge of +2. We therefore need to add electrons to the most positive side so that charges balance, and therefore if we add 5 electrons, each having a negative charge on this side, the charges on both sides now equal +2. Let's now use the oxidation number method, but before we do that we must balance for atoms. So our 4 oxygens here become 4 waters on this side, and our 8 hydrogens become 8 H plus on this side. So let's now work out the oxidation state of the manganese on the left hand side. So when we add the atoms up, the overall charge, which is -1, must equal the charge on the ion. We've got 4 oxygen atoms, and therefore each oxygen atom has an oxidation state of -8. The overall charge is equal to -1. Manganese therefore has an oxidation state of +7. So this is the manganate 7 ion. Manganate 7 ion. Here the oxidation state of the manganese has gone down to +2, and therefore manganese has gone from +7 all the way down to +2, and therefore it has taken 5 electrons. So by reducing, the electrons are added on this side. We're now going to combine half equations. And in combining half equations, we will now form full redox equations. So in your independent study book, you're asked to combine the 2 half equations here, with this ion turning into this ion and iodine becoming iodide. So we've already balanced these 2 half equations. So let's now write those out as balanced half equations. So in the first half equation, we can see there's been an oxidation because electrons have been lost because they're appearing on the right hand side. Here we're balanced for atoms. Iodine has got, we've got 2 iodine atoms on this side and 2 iodide ions on this side. Now we just need to check for charge, and we need to add electrons to the more negative side, sorry, to the more positive side, which is the left hand side. This is a reduction reaction. Now to add the 2 half equations together, we need to check that the electrons balance on both sides. So here, the reducing agent, which is this ion, the thiosulfate ion, is giving up electrons. The reducing agent becomes oxidized. In this case, therefore, the iodine is behaving as the oxidizing agent because it's taking electrons and becoming reduced to iodide. So we always have On the reactant side, on the left hand side, an oxidizing agent and a reducing agent, and the electrons must balance. So electrons in the half equations must appear on either side. We must have one species becoming oxidized and one species becoming reduced. If species appear on both sides, they can cancel out. The electrons in a balanced redox equation must always cancel out. So now our overall balanced equation ignores the electrons, and this is a full redox reaction. We know it's a redox reaction because we saw that this iron became oxidized and the iodine became reduced to iodide. We can check for charges to check it's balanced also. On this side, the overall charge is 2 times minus 2. So the overall charge on this side is minus 4. On this side, we have minus 2, and 2 times minus 1, which is a charge of minus 4. It's balanced for atoms and it's balanced for charge. Let's try some more. So are you able to write a full redox reaction for when sulfuric acid reacts with bromide ions? Well, let's first of all balance the half equations. You can see that on this side we have 4 oxygens, and therefore we only have 2 oxygen atoms on here, and yet we only have 1 sulfur. So the only thing that we can do is to add water to that reaction. So that forms 2H2O. We have now increased the number of hydrogen atoms on this side. We have 4 on this side and 2, so it follows we must have 2 hydrogen ions on this side of the equation. Now let's check the charge. On this side we have an overall positive charge and no charge on this side. We have an excess of a 2 plus charge on this side, so we therefore need to add 2 electrons to this side. So it looks like the sulfur in the sulfuric acid is being reduced. If we check the oxidation states, in sulfuric acid, sulfur has an oxidation state of +6 and +4, and yes, it has gained 2 electrons to become reduced. So we know that that one is balanced. Let's now look at the bromine. Here we've got 2 bromine atoms on this side, and therefore we need to have 2 bromide ions on this side of the equation. The overall charge on this left hand side is 2 times minus 1, which is minus 2, and on this side it's 0. We need to add electrons to the most positive side, which is this side, so we need to add 2 electrons to this side. This is handy because both equations now have, in this case, the reduction is gaining 2 electrons and the oxidation is losing 2 electrons. So we now almost have our full balanced equation. However, electrons are appearing on both sides, which they shouldn't in a full redox reaction. So since there are 2 electrons on both sides, we can take away 2 electrons from both sides. And now we have our complete balanced redox equation. The sulfur in the sulfuric acid has been reduced and the bromide ions have been oxidized from -1 to the element 0. It's a balanced redox reaction. Let's try a more complicated one. So first of all, let's balance the 2 half equations where iodate ions are becoming iodine and nitrate ions are becoming nitrate ions. So these old name for these are nitrite becoming nitrate ions. So let's balance the top one first of all. Let's balance for atoms. You can see here there are 2 iodine atoms on the right hand side, so we need 2 iodine atoms on the left hand side. We now have introduced 2 lots of 3, which is 6 oxygens. And remember, oxygens have to become water on the other side. So we're now going to introduce 6 moles of water onto this side. Now we've introduced 6 moles of water onto this side, we have now introduced hydrogen atoms, which must become hydrogen ions on the other side. So we now have 12 hydrogen ions on the left hand side. Now let's check for charge. On the left hand side we have 12 times plus 1, which is plus 12, minus 2, which is an overall charge of minus 10. And on this side we have got no charge at all. So since the left hand side has an overall positive charge, we need to add 10 electrons in order to cancel that out. So the iodate has been reduced to iodine. We can check that using the oxidation numbers. So if we look at the oxidation state of iodine in iodate, oxygen is always minus, let's do this at the side. So oxygen is always minus 2 and the overall charge on the ion is minus 1. So iodine minus 6 equals minus 1. Iodine has got an oxidation state of plus 5. So iodine has been reduced from plus 5 to 0. Let's now look at the nitrite ion here. So already we're balanced with nitrogen, but we've got one too many oxygens on this side. So therefore that must form H2O on this side. So we add a molecule of H2O on this side. So now balanced for oxygen, but now we've got an excess of hydrogens. So now we need to add 2 H pluses on this side. If we now use the balancing charges rule, on this side we've got an overall charge of minus 1, and on this side we've got an overall charge of plus 1. And therefore to balance out for electrons we need to add 2 electrons to this side. Let's do that checking oxidation numbers. So in our NO2 minus ion, remember that oxygen is always minus 2, so the overall charge on the ion is minus 1. Nitrogen in NO2 has got an oxidation state of plus 3. In NO3, however, let's check that, nitrogen has got an overall oxidation state of plus 5. So its oxidation state has gone from plus 5 down to plus 3. It has been reduced, and so it has therefore been, plus 3 to plus 5. It's therefore been oxidized and lost 2 electrons. Now we have an imbalance of electrons. So what we need to do is to make sure that we have the same number of electrons in both the oxidizing reaction and in the reducing reaction. So this is reduction because electrons are being gained, and this is oxidation because electrons are being lost. Now the reducing agent is giving up 10 electrons, and that means we have to have enough oxidizing agents to accept those 10 electrons. So what we must do is multiply the whole of this equation by 5, and that will then give us 10 electrons. So if we multiply 2 electrons by 5, that means now we have got 10 E's. However, we need to now multiply everything else through by 5. So that's 5 H2O's, 5 NO2 minuses, 5 NO3 minuses, 2 times 5 is 10, and that gives us a total of 10 hydrogen ions on this side, 10 H+. Only when you are balanced for electrons on the oxidizing side and the reducing side can you add the two half equations. Well, let's first of all cancel out the electrons on both sides, because we don't need to bring them down, because we know in the final redox reaction they cancel out. So on this side we have got 12H+, so we have 12 hydrogen ions, and we also have from the top 2 lots of iodate ions, 2 IO3 minus ions. We now need to bring down these, so that's 5 H2Os and 5 NO2 minuses. and the electrons have cancelled out. Let's now look at our final equation. You can see clearly on both sides of the equation we have got hydrogen ions. We've got 12 here and we've got 10 here. If we take 10 hydrogen ions from both sides, that cancels out completely the hydrogen ions on this side and leaves us with 2 hydrogen ions on this side. We can also look at both sides and see water. On this side we have got 5 water molecules and this one 6. So if we take out the 5 water molecules from both sides, that leaves us with 1 water molecule on this side. So now let's tidy up our balanced redox equation. So again, remember, electrons should not appear in the overall redox equation. We've checked our atoms, let's now check the charge. So on this side we've got +2, -2 and an overall charge of -5 on the left hand side. On the right hand side, 5 times -1 is -5. The charge is balanced, the atom's balanced, and you have an overall balanced redox equation. In this next section, we'll be naming compounds and ions. In your independent study booklet, you're asked to give the following names of these compounds and ions. So the first one, let's look at how we would name A. It's MnO4-. MnO4-. The first thing you need to do is to find the oxidation state of the element here, because we know that oxygen always has an oxidation state of -1. So going through our rules, we know that if we've got 4 lots of oxygens and the sum of the oxidation states of the elements is equal to the charge on the ion, then manganese plus 4 lots of oxygen, which is -8, equals -1. We add 8 to both sides, and therefore we know that manganese has got an oxidation state of +7. And therefore we know when anything has oxygen is attached, we use the suffix -ate. And therefore the name of this ion is manganate because of the oxygen. And then in Roman numerals we use VII for 7. So the oxidation state of the manganese appears as Roman numerals in brackets after the name of the ion. This time we don't have an ion, we have a full compound. And obviously the element here is potassium, then we have chromium, and we have oxygen. And these two have fixed oxidation states, and therefore we're looking to find the oxidation state of the chromium. So we'll do that as normal. So potassium has got an oxidation state of +1, and there are 2 of them, and therefore the sum of the 2 potassium ions is +2. We're trying to find chromium, and we also have 4 oxygens, and we know every oxygen has an oxidation state of -2, so that's -8. The overall charge, because it's a compound, is 0. There is no charge. So now chromium +8 - 2 is -6 equals 0. Chromium therefore has an oxidation state of +6. So the name of this compound is potassium chromate, because it's got oxygen attached. And remember the suffix -ate for oxygen. The oxidation state of chromium is 6, so that's 6 in Roman numerals. Potassium chromate 6. So let's now look at iron 2 sulfate. We've been told that the oxidation state of iron in this compound is 2. There is no overall charge, so we bring down the oxidation numbers. Iron is +2, sulfur we don't know, and 4 lots of oxygen is -8, and the overall charge on the compound is 0. Sulfur -6 equals 0, and therefore sulfur has an oxidation state of +6. And therefore the name of this compound is iron Roman numerals 2, denoting the oxidation state of the ion, sulfate, oxidation number 6 in Roman numerals. Here's the word of the day, disproportionation. So we're going to look at some common disproportionation reactions in chemistry. So let's look at hydrogen peroxide. In the first equation, hydrogen peroxide is forming water. So let's balance this equation in the usual way. Where we've got oxygens on one side, we form water on the other side. And therefore we have got 2 oxygens on this side, and so we need to double the equation to make 2 waters on this side. Now we have an excess of hydrogen ions, and the excess of hydrogen ions occurs on the right hand side. So now we need to add 2 H plus ions onto this side of the equation. Now we need to balance the charge, and there's an excess of positive charge on the left hand side, so we add 2 electrons on this side. Let's now have a look at the scenario where hydrogen peroxide breaks down to form oxygen. So on this side we've got 2 oxygens, and on this side we've got 2 oxygens, but now we have an excess of hydrogen on this side, and therefore we need to turn those into H plus ions. To balance out this equation, there's an excess of hydrogen ions now on the right hand side, so we need to add 2 electrons. When we add these 2 equations together, the electrons cancel out on both sides, so we'll cancel those electrons out here and here. Then we can bring all of the other substances down. But notice we also have hydrogen ions appearing on both sides, so we can cancel those out. So the overall redox equation is 2 lots of hydrogen peroxide forming 2 moles of water and 1 mole of oxygen gas. One of the hydrogen peroxides has gained electrons, or rather the oxygen has gained electrons, because in peroxides, oxygen has an oxidation state of -1, and now it's gone to -2. So this, because it gained electrons, is a reduction reaction. The oxygen became reduced. In this half equation, however, the oxidation state of oxygen is -1, but it goes to 0. It's gone up the ladder, and therefore this is an oxidation reaction. And in this unusual circumstance, the hydrogen peroxide in this case, because itself was being reduced, is behaving as an oxidizing agent. And in this case, it's behaving as a reducing agent. And in both cases, the oxygen has been simultaneously oxidized and reduced. And this is called a disproportionation reaction. So now we're going to look at a common example we find with chlorine and its compounds. Have you ever wondered what's in bleach? Well, if you mix sodium chloride and chlorine, you end up with a compound called sodium chlorate, NaClO. Now to finish balancing this, the chlorine atom must also react with another sodium atom, a sodium ion, to form sodium chloride. And to finish balancing this off, because we've got 2 sodium atoms, we also therefore need to form water. Now the chlorine in sodium chlorate has got an oxidation state of +1, and in sodium chloride it's got an oxidation state of -1. The chlorine has been simultaneously oxidized to +1 and reduced to -1, and we call this a disproportionation reaction. Now let's have another example of what happens if you put chlorine into a swimming pool. When you put chlorine into a swimming pool, the swimming pool contains H2O. The chlorine reacts with the water to make hypochlorous acid, or chloric acid 1, again where the oxidation state of chlorine is +1. We actually also form another acid, which is hydrochloric acid, and it's the hypochlorous acid which reacts with the bacteria and kills them. Now an interesting reaction happens when we have chlorine and water in sunlight. Let's see if you can balance the equation if I give you the two half reactions. So the water actually gets oxidized to oxygen gas, and the chlorine gets reduced to chloride ions in the presence of sunlight. Could you write an overall balanced equation for this reaction? Pause the video, work it on paper, and then check your answer. So let's all balance the reaction of water getting turned into oxygen gas. Well, as usual, we've got too many oxygen atoms on this side, so we need to double. So we've got two oxygens on this side and only one here, so we need to double this side. That has now introduced hydrogen ions, so they must appear on this side as 4 H pluses. Now we need to balance for charge, and remember we add electrons to the most positive side, so we need to add 4 electrons to this side. Chlorine atoms on this side becoming chloride ions, well, we need 2 moles of chloride ions. Now this is the more positive side, so we need to add 2 electrons. But before we can add the oxidation reaction to the reduction reaction, we need to balance for electrons. So therefore we need to times this half equation by 2. And that means we now, instead of having 2 electrons, we have 4 electrons here, times the chlorine molecules by 2, and we now have 4 chloride ions here. We can now add together the two half equations to show us what happens to chlorine and water in the presence of sunlight. So we have 2 water molecules and we have 2 moles of chlorine molecules reacting to form oxygen gas and 4 hydrogen ions and 4 chloride ions, which makes 4 moles of hydrochloric acid. This is not a disproportionation reaction because the chlorine has got an oxidation state here of 0 and it only gets reduced to the oxidation state of -1. So here's a past paper question. All of these can be found on Google Classroom in the answers to the caboodle questions. But let's look at part D. Lead 4 oxide reacting with concentrated hydrochloric acid to produce chlorine, lead ions, Pb2 plus ions and water. So this time we're given words and we need to write half equations for the formation of Pb2 plus from PbO2 in the presence of hydrogen ions. So the first thing you need to do is we are forming Pb2 plus, and the arrow here means forming. So we're forming Pb2 plus from PbO2. So we know that if we've got oxygen on one side, we need to turn that into water, so that forms 2H2O. Now we have an excess of hydrogen atoms and they become hydrogen ions on this side. We now check for charges and we can see that the overall charge on this side is +4, whereas on this side it's +2. So we now need to add electrons to the most positive side, which is this side, and we have balanced that half equation. Now it says write a balanced equation for the formation. So we put an arrow of chlorine from chloride ions. We've got 2 chlorine atoms on this side, so we need 2 chloride ions. We now add electrons to the most positive side, which is this side. And now it says deduce an equation for the reaction, and that means we simply add the 2 half equations together, cancel out the electrons to get our full balanced equation. So we've got our concentrated hydrochloric acid, we're forming lead ions and chlorine. Check our charges. On this side the overall charge is +2 and the overall charge is +2 on this side also. In this exam question, again you're given the names of the species. So an acidified aqueous solution nitrates 5 ions reacting with copper metal forming nitrogen monoxide and copper 2 ions. First of all, write an equation, half equation for forming copper to copper 2 plus ions. So copper metal forming copper 2 plus ions, we simply balance the charge and then we add our electrons on by adding electrons to the more positive side. So now write a half equation in an acidified solution of nitrate ions to form nitrogen monoxide ions. So we know that nitrate 5 ions, NO3 minus, are forming nitrogen monoxide, and they've told us that is NO. Now let's balance this half equation. Here we've got 3 oxygen atoms, here we've only got 1. So therefore we need to add 2 moles of water to this side to balance that half equation. However, now we've got an excess of 4 hydrogen atoms, and these become 4 hydrogen ions on the left hand side. Let's now check our charge. The overall charge on this side is +4 minus 1, which is +3, and no charge on this side. So now we need to add 3 electrons to the more positive side to balance out the charge. Now we can see that this half equation here is giving up 2 electrons. Our oxidizing agent, our reducing agent, is giving up 2 electrons, whereas our oxidizing agent needs to take 3. In order to balance up the electrons, we need to multiply the reducing agent by 3, and we need to multiply the oxidizing agent by 2 to give a common number of electrons. So that now gives us 6 electrons, but we need to times this one by 3 and also this by 3. Now, to balance up electrons here, we need to times that by 2, and that gives us 6 electrons here. But we also need to times that by 2, and we also need to double the number of nitrate ions, nitrogen monoxide, and water molecules before we can add the 2 electron equations together. To add the 2 equations together, we can now cancel our electrons out and bring the reactants down, which is 8 hydrogen ions, which is 2 nitrate 5 ions, 3 copper metals on the left hand side, and on the right hand side we're forming 3 moles of copper 2+ ions, we're forming 2 nitrogen monoxide and forming 4 H2Os. Let's check our charges. On this side the overall charge is plus 6. We've got +8 minus 2 is +6, and on this side the overall charge 3 times +2 is also +6. We're balanced for atoms, we're balanced for charge, and we've written an overall equation for the reaction.